Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at networks and graphs, which are exactly the same thing. These two words are used interchangeably in maths. So what exactly is a network or a graph? Well, it's basically just a collection, a set of vertices and edges. The edges connect the vertices. So here is a network drawn. This network has 1, 2, 3, 4, 5 vertices. So we write this, the set of V contains 5 elements, A, B, C, D, and E. Each of these is called an edge. This is just one edge. So this again has 5. The number of edges we write like this is equal to 5. So really important is the degree of a vertex. The degree of a vertex is the number of edges emanating from that vertex. So for A, we actually count this one twice. This is called a loop, an edge that connects a vertex to itself. So there are 1, 2, 3, 4 edges emanating from A, so the degree of A is 4. On the other hand, the degree of B is 2 because there are 2 edges emanating from B. So this graph here is called an undirected graph. It's not directed because there are no direction lines on this edge. That means you can travel in both directions along an edge. This graph is what we call disconnected. Connected means that it's possible to get from any vertex to any other vertex. Here, that's not possible. You can't get from E to anywhere else. You can't get from any of these to E. E is what we call an isolated vertex. That means there are no edges connecting to it. Now, D is called a pendant because it has degree 1. See, it's hanging out there like a pendant. So some graphs also have cycles. It's very important to know that in many contexts. A cycle is something like this. It's basically like a closed path where no edges are repeated. A, B, and C form a 3 cycle because there are 3 vertices in this cycle. As I said, that will become very important. Now, I'm going to define walk, path, and trail, but the problem is there's actually great variability between textbooks as to these definitions. So, for our purposes here, a walk is just any traversal of a sequence of vertices. So, A to B is a walk, A to B to C to D, that is a walk. A path is a walk in which there are different vertices and edges. So something like A to B to C, that's a walk. A trail is just a walk where you don't repeat any of the edges. So A to B to C to D, that's a walk. Again, there is a lot of variability in these definitions. Now we say that 2 vertices are adjacent if they're connected by an edge. So A and B are adjacent, A and D are not adjacent. A vertex is reachable from another if there's a path connecting them. So even though A and D are not adjacent, they are connected because I can go A, B, C, D, or just A, C, D. On the other hand, A and E, they're not connected, so A is not reachable from E, E is not reachable from A. So we can represent the concept of adjacency in an adjacency matrix. So when we're making the adjacency matrix that I'll call M, we list the vertices down a column and a row, and that's just because there's no necessity that they have to be in order. So what we're going to do is fill the matrix with edges that are emanating from one vertex to another. So from A to A, we actually have 2 here because we can go here or here. So from A to B, there is 1 edge, so we put a 1 here. There's 1 edge from A to C and none from A to either D or E. Let's do the same for B. There's 1 from B to A, none from B to itself. There's 1 from B to C and none from B to D or E. And we go on like this. So for an undirected graph like this, the adjacency matrix is always symmetrical. Now, this also helps us with the concept of reachability. See, the adjacency matrix tells us if a vertex is reachable in one step from another vertex. So we can see we can't get from A to D in one step. But m squared will tell us if a vertex is reachable from another in 2 steps. M cubed will tell us if it's reachable in 3 steps, and so on. All right, let's now look at an example of a directed graph. So this graph here is directed because travel is possible in only one direction along each edge. Now, this particular directed graph has a vertex known as a source. So a source is one that has edges going out from it, but none into it. On the other hand, it has a sink here at D, a vertex where vertices go into it, but not out of it. So when we're looking at the degree in a directed graph, we look at the degree coming in and the degree going out. So A has in degree 0 because no vertices are going towards A. It has out degree 2 because there are 2 vertices going out from it. And we'll use that to draw the adjacency matrix for the directed graph. So out degrees go across here. So A doesn't go out to itself. A does go out to B. It does go out to C. So that's why we have that row. And then we look at B. We look at the vertices going out from B. So B only leads to D. So all of the other entries will be 0. And then we complete for the other rows. So here we see A is a source because there are no vertices coming into A, and D is a sink because there are no vertices going out from D. Once again, we can calculate m squared, m cubed, etc. to find which vertices are reachable from which others in n steps. Now, just a point here, A is not an isolated vertex, because even though it has an in degree of 0, it has a positive out degree. Isolated vertices are totally disconnected, as we saw in the previous example. Now let's look at Eulerian and Hamiltonian paths. So an Eulerian path, sometimes called an Eulerian trail, again there's a lot of variability in these definitions, but what it is just a path that visits every edge exactly once. So if you have such a path that starts and ends at the same vertex, it's called an Eulerian circuit. So these are nice to work with because there is a necessary and sufficient condition here for when you can or can't have Eulerian paths and circuits. So let's look at this one and determine whether an Eulerian path and circuit is possible. So to do this, we look at the degrees of each vertex. So A has degree 2, degree 3, 2, 3, and 2. In this one, there are exactly 2 vertices of odd degree. That means an Eulerian path is possible, but an Eulerian circuit is not. So as it says here in orange, if I want to draw an Eulerian path, I need to start at one of the vertices of odd degree and finish at the other. So let's draw the path. Let's just start at B. We'll go here, 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 here. You can see I started at B and ended up in D. Now, Eulerian paths are not unique. I could have started D. There are other paths, but that is one such Eulerian path. Let's look over here now. So I've added in this extra vertex. So now A has degree 3, E has degree 3, as do B and D. So we failed the condition that there can only be 2 vertices of odd degree. So here an Eulerian path is not possible, and that also means an Eulerian circuit is not possible. On the other hand here, every vertex has degree 2. So an Eulerian circuit is possible. I can start at any vertex I like. So I could just go here. This is an Eulerian circuit. A to B to E to D to C and back to A. So Hamiltonian paths and circuits are harder because there is no necessary or sufficient condition. So Eulerian paths visit every edge exactly once, Hamiltonian paths visit every vertex exactly once. But it's not clear from looking at the graph whether or not a Hamiltonian path or circuit is possible. So if we look at this one here, we just have to try our luck. So if I want to visit every vertex exactly once, I could just go A to E, back to B, to D, to C, and back to A. That is a Hamiltonian circuit. But again, it can be complicated to determine if one is possible at all. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.